Welcome back, everyone, to this last video on Chapter 2. So, let's have a little recap. So, up till now, there's a few tools we've used. There's a resultant vector that's equal to the sum of all the forces. Forces are sliding vectors. That describes the way they can be repositioned. Remember, we talked about along the line of a force. Okay, and moments some moment about O, and this R is a resultant. So it's the resultant moment about the point O, which is the sum of all the moments about O, and this really shouldn't have a sum there. And moments and couples are free vectors. They affect the entire object, so they can be moved anywhere on the object. So, like if you have this rectangular object here, oh, let's make that a little neater. Here, there. Okay, and we're going to do that again. Right here. Those look pretty similar. Okay, so in this one on the left, we have a moment here. And in this case, the moment is applied here. All right. And you can think of this as oh, here's an arm coming out of this, and there's a force applied to that. Okay, so the force applied to the arm produces a moment, whatever the mechanism is. Okay, these two are equivalent. Moment does not have a location. It's a tendency to have the whole object rotate. So what that says is that M, it helps you to solve the problem because M can be positioned anywhere. Anywhere on the object. Okay. Oh, well, little caveat. As long as we keep magnitude and direction the same. And direction the same. Okay, so the thing about force that differs from that is force has a location that determines the magnitude and direction of the moment. That's the moment arm, basically, right? So a force has a location that determines the magnitude and direction of the moment produced. But moment has no specific location, right? Moment is, as we said before, a free vector and applies everywhere on the object. Okay, so let's use that. So we're going to take this funky looking bracket. Rigid attachment down below. I'm going to start here and go up to here. I'm going to do another one of those. It basically can be like a cross. Just so you know ahead of time what we're getting at here. And then I'm going to go out to the sides. And again. Yep, line. 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 Up. There. There. And then close these off. Let's fix that up a little bit. Okay, almost done here. Two more little lines from here to there. Doesn't like little lines apparently. We'll have to fix that up. Okay, so we'll go back here to our little eraser and clean that up, clean that up. Okay, there. Okay, good enough. You get the idea there. Okay, so this is a complicated little thing. Probably should have drawn it bigger, but that's what it is. Here, right here, we're going to have a point O. Okay, so forces. Forces and moments. Let's see, we need an arrow going this way. Okay, this one is 300 newtons. Okay, then, oops, back here. Okay, here, let's speed this up a little bit. Here, let's put a horizontal reference line, and then this guy is at 60 degrees, and this is 500 newtons. Then over on the left side, we have a force of 200 newtons. And we have a moment about here of 600 Newton meters. And this, just to be clear, is in the XY plane. And let's see. So let's call this 1, call this 2, and call this 3 the forces. Okay, let's get some dimensions on here. Here to here is 300 millimeters. From here to the ground, or the rigid attachment, is 400 millimeters. And then we need a couple horizontal dimensions here. From here, to there. Is 450 millimeters. And again, on the other side too. 450 millimeters. Okay, so find, nope. Find the resultant force and moment. Okay, so the resultant force, which is what they're asking for, is the sum of all the forces. So let's break that into components. We're going to do x direction first. So the x component of the resultant is the sum of all the x components of all the forces. So we have 2. We have force number 2, which is 500 newtons times the cosine of 60 degrees plus 300 newtons, which comes out to 550 newtons. The resultant force in the y direction is the sum of all the forces in the y direction, which is 200 newtons plus 500 sine of 60 equals 630 newtons. Okay, so we're going to need to oppose these when we design for static equilibrium. So, but for now, let's move on to finding the sum of our moments. Okay, so we need to sum all the moments, but we need to pick a location to find the resultant about. Now, in the end, you don't want moments anywhere in the object. The moments should equal 0. This is statics. Right? But for now, we're going to pick point O, because you got to pick something. Okay, and that's the point of rigid attachment. So we're going to find the resultant moment, and again, the resultant moment is the sum of all the moments. So we got a few of these. There's 4 parts to this. First, we have a minus 200 times 0.450. This is meters. K direction. Okay, so negative because it's clockwise. Remember our convention, counterclockwise positive, clockwise negative. Okay, so this is due to force 1. Okay, next one, minus 500 cosine 60 times 0.7 K, and these are in units of Newton meters. All right, and this one is due to force 2. Minus again 300 times 0.400 K again, due to force 3. All right, so these are all clockwise, which gives the negative, right? Because they're summing moments. So we just put whatever sign is appropriate for the direction. And then lastly, there's the minus 600 Newton meters which is the applied moment. Now, when you do the algebra and sum all those up, the sum of the moments equals minus 985 Newton meters. Okay. So, remember we had Rx equal to 550 newtons, Ry equal to 630 newtons. Okay, so now we have to put our resultant force about the point which you took the moment. So place your force, the resultant force, resultant force at the point about which you took the sum of the moments. For us, that's going to be point O. Okay. If you don't do that, you're causing another moment. All right. So, quick sketch again here, rigid attachment, and I'm just going to freehand this one. Okay, here. Okay, so the resultants are both positive, so it's going to be going off this way. And it's going to be clockwise, the resultant moment. So that's the resultant force and the resultant moment. acting on this bracket. The convention, you can put the moment anywhere, right? Because it's a free vector. But convention is to put it about the point that the resultant vector acts. So let me just write that. Convention is to place the moment about the point about which the moments were summed. Okay. So now, for static equilibrium, you have to oppose these.